Thank you, John, and good afternoon to everyone, or indeed good morning, or perhaps even good evening, depending on where you're joining us from. So John said the webinar today is looking at why density is important in flow measurement for liquids and gases. And so over the next hour or thereabouts, I'm going to answer that question, hopefully. And as John said, obviously, at the end of it, if there are questions, we'll try to answer them. If not, we will take note of them and get back to you. Okay, so what am I going to cover? I'll say a little bit of introduction about density and why it's important to flow measurement for liquids and gases. We'll have a look at the various techniques available for measuring density of gases and liquids. And then I'll touch on some calculation methods which are also used particularly for liquids, and summarize that at the end. And then, as I say, hopefully we'll have some time for questions and answers at the end. So in many process applications, density is actually used for process control, and it's often used as well for product quality assessment. Similarly, accurate flow measurement is vital throughout process industry. In fact, most processing of materials takes place in the liquid phase. Although we live in a solid environment and we think of everything around us as being solid, even many of these things are actually processed in the liquid stage at some point. So flow measurement of liquids and gases is absolutely vital throughout process industry, and obviously also in primary energy production. Now, depending on the technology used, flow rate may be measured by mass or by volume, but there is often a requirement to convert between these quantities. To do that requires a knowledge of the density of the fluid as a function of temperature and pressure. So in that case, density becomes a fundamental part of a flow measurement system. Which then brings us to the question, what is density? Density is simply the mass per unit volume of a fluid, a gas or a liquid. So in the SI system of units, the unit of density will be the kilogram per cubic meter, mass divided by volume. So one equation, nice and easy, and that's all. You'll be glad to know. Well, yes, okay, there's some equations here, but really this is just illustrating some related points. The previous slide gave the definition of density in terms of its base units in the SI system, kilograms per cubic meter. But you'll often come across other ways of referencing density. Relative density or specific gravity is used. Relative density, specific gravity, is the density of the fluid divided by the density of a reference fluid, and the reference must be at stated conditions. So often for liquids, water is used as the reference fluid, and the reference conditions are typically at standard atmospheric conditions, 1.01325 bar absolute, and usually 4 degrees Celsius, but other temperatures are used. For air, the reference fluid is often, for gases, the reference fluid is usually air, again at standard atmospheric pressure, 1.01325 bar, but usually 0 Celsius. Again, however, other temperatures are used. So if you are dealing with relative density or specific gravity, then it's vital that you know what the reference fluid is and what the reference conditions are. It's also worth pointing out that relative density or specific gravity is not a density ratio. A density ratio is the ratio of the density of the fluid at the conditions you're interested in to the density of the same fluid at reference temperature and pressure conditions. There are other terms used as well, such as proof or API gravity, and there are interconversions between those. So the bottom equation there shows the relationship between the API gravity and specific gravity, and then from the equation for specific gravity, you can obviously get back to density. And different industries use these. API gravity, of course, is widely used in the oil industry. Proof is typically used in the food and drink sector, most specifically usually in connection with alcoholic drinks. So that's what density is. How do we measure it? What are the techniques that are available for measuring density, and what are their advantages and disadvantages? You can basically split density measurement techniques into two categories: offline methods and online or inline methods. And I'll look at these in turn, and we'll look at some of the issues associated with them. But whichever technique is used, calibration is important. And in particular for the online and inline methods, if these systems are forming part of fiscal measurement systems, then correct calibration, appropriate calibration of these online or inline instruments is absolutely vital to ensure the performance of the complete measurement system. So how do we determine density? Well, if we take a step back and think of flow measurement, flow rate, the primary standard way of measuring flow rate is essentially a bucket and a stopwatch plus a set of scales or a ruler. So flow rate, of course, is a quantity, either kilograms or cubic meters per unit time. So you can either weigh the amount gravimetrically, so you weigh the bucket before and after filling it, you measure the time it's taken to fill it, you've got a mass per unit time. Or you do it volumetrically, where you measure the change in the level of liquid in the bucket. You then have a volume and a time, so you have a volumetric flow rate. Density, of course, combines both of those. It's kilograms per cubic meter. So the primary standard way of determining density would be gravimetric. You weigh the bucket empty, fill it with the fluid whose density you want to measure, and weigh again. You have a mass and a volume. Of course, in that simplistic description, that would only work for liquids, but with a closed vessel, you can do it for gases. So the primary measurement for density would be gravimetric. In practice, of course, we use a range of techniques depending on what we're trying to achieve, whether we are trying to achieve a reference quality measurement, something approaching a primary standard, or whether we are interested in a production environment where ease of measurement, speed of measurement is often more important than the ultimate performance in terms of low uncertainty. So I'm going to look over a number of techniques which are used and some of the ways they can be implemented, and discuss some of the advantages and disadvantages of the different techniques. Hydrostatic techniques, basically you measure the apparent weight of a body of known mass and density when it's totally submerged in the test fluid. And the basis for this is Archimedes' principle. When a body is totally submerged in a fluid, it is subject to a buoyant upthrust from the displaced fluid by its mass. And if you know the mass of the body and its density, from which you can calculate its volume, you can calculate the density of the fluid that it's in. In terms of implementation, there's basically three variants on that. Mechanical suspension systems, where the body immersed in the fluid is connected to a balance by a fine wire. Variant of that is where the body is connected to the balance by a mechanical coupling, typically through the wall of a pressure vessel. And the third variant is where the body in the fluid is held in equilibrium by an electromagnetic field. What does that look like? Here's a diagram of a magnetic suspension system using an analytical balance to determine the apparent weight of the body. So the equation is the basic form of the equation relating the density of the fluid to the true vacuum mass of the body immersed in it, the apparent mass when it's immersed in the fluid, and its volume. We have to apply other corrections, of course, to account for temperature and pressure effects on the body, the vessel it's in, etc. But that's the basic principle. So it's very close to a primary standard method of measurement as well. Hydrostatic techniques have a number of advantages. They can be automated, and depending on the implementation, can be used over wide temperature and pressure ranges. The type with the wire suspension is limited to close to ambient temperature and ambient pressure. The magnetic coupling system that I showed on the previous slide, and the type where the body is held in suspension by an electromagnetic field, can be used at elevated temperatures and pressures. They are very, very accurate. You can achieve uncertainties down to something of the order of 0.005% or possibly better, depending on the implementation. And as I mentioned, they are essentially a primary standard method. They are in practice as close as we get to a primary standard method for density measurement. And they can be used for both gases and liquids. It requires a bit more care for gases because gas densities are much lower, so the buoyant upthrust is less, and you need to think about how to design it to take account for that. However, they have disadvantages, as do all techniques. To achieve the sort of accuracy I was mentioning there, to get down to those uncertainties of 0.005% or so, requires careful design and careful operation. And that tends to mean that these systems are time-consuming to operate unless they are automated. Unfortunately, they tend to be expensive to automate because of all of the secondary bits that are required when you're trying to achieve such low uncertainties. And big disadvantage really is that they are certainly not suitable for online or inline use. They are primary standard laboratory instruments, not even just routine calibration lab instruments. They are really primary standard type devices. So what else can we do? Well, we can use pycnometry, where you measure the mass of a known volume of fluid. And again, there's a number of ways that can be implemented. So capillary stoppered pycnometers, where you compare the masses of equal volumes of the fluid whose density you want to measure, and a reference fluid. I've said water here because water is the most commonly used reference fluid, mainly because we know the density of water as a function of temperature and pressure very, very accurately. Round about ambient conditions, the best equation for the density of water has an uncertainty down in the 0.001 to 0.002% level. So water is the natural reference fluid there. Slightly different implementation of a pycnometer is a graduated bicapillary, again calibrated using water, where you're looking at levels. And pycnometry can also be done at pressure using pressure pycnometers. Again, these are most commonly calibrated with water. What do these look like? On the left, we've got the capillary stoppered pycnometer, and what you do with that is you fill it first with water and weigh it. Weigh empty, fill with water, weigh again, so you have a mass of water. The capillary stopper arrangement is a means whereby you can guarantee that you've filled it to the same level every time with no air present. So, a simple technique, but fairly close to primary standard effectively. You're measuring a mass and a volume. Graduated bicapillary pycnometer in the middle, again, is calibrated using water, and then you fill with the fluid whose density you're interested in and measure the mass and note the levels from which you can get a volume and a mass. And the image on the right shows a typical pressure pycnometer, which is basically a pressure vessel with inlet and outlet connections, allowing you to take a sample from a pressurized line, either of a gas or a liquid. Again, like the hydrostatic techniques, there are a number of advantages and disadvantages. The pycnometers are fairly fundamental, very, very close to primary standard, and in fact, you can implement a primary standard system using a pressure pycnometer arrangement, for example. They are simple, certainly for the capillary stoppered pycnometer, and for that too cheap to purchase. They can also have good to high accuracy, or in fact very, very high accuracy, low uncertainty if you go to the sort of levels required for a primary standard approach. And again, they can be used for gases and liquids. The glass units obviously are restricted to liquids at ambient conditions or close to ambient. Pressure pycnometers can be used for gases and liquids at elevated conditions. Similarly to the hydrostatic techniques, careful design and operation is required if you want to get very, very low uncertainties. And again, that tends to mean that it becomes time consuming unless you automate. As with the hydrostatic techniques, automation becomes expensive if you are really chasing the lowest uncertainties. And again, like the hydrostatic techniques, they're not suitable for online use. Pressure pycnometry is at most a sampling technique. So, two major techniques we've looked at, neither of which are suitable for online or inline use. What is? The most commonly used technique is oscillation, to measure the oscillation period of a body. And that can be either a vibrating tube, where you measure the oscillation period of the tube filled with the fluid whose density you want to determine, or by measuring the oscillation period of a rod or a tuning fork immersed in the fluid whose density you're interested in measuring. Implementations are slightly different, but the basic principle is the same. The density of the fluid will influence the oscillation period, and so from a measurement of the period, you can calculate the density of the fluid. Insertion densitometers typically are inserted either directly into the fluid or perhaps into a pocket in the fluid or in a side stream, and can be of either type, a tuning fork arrangement or thin-walled cylinder. Laboratory densitometers and online densitometers are usually tube-based with the fluid in the tube, either static within the tube as in the laboratory densitometer shown here, or flowing through the tube. But whichever design, the principle is the same. The tube is driven in transverse oscillation, and from the period signal you can calculate density. So on the left we have an example of a flow-through vibrating tube densitometer. Fluid flows through the tube and the tube is driven in transverse oscillation. Period of oscillation is measured. Modern Coriolis meters, of course, also provide a measurement of density by driving the tube in transverse oscillation, not in the Coriolis twist mode, which is used for flow, but the transverse oscillation from which, again, you can calculate density. Oscillatory techniques have a number of advantages. They are simple and they can be easily automated. They can also be used over wide temperature and pressure ranges, and crucially, they can be used inline and online. There are a wide range of these available commercially, and they are potentially very accurate. You can achieve uncertainties down into the 0.02% level with careful operation. And again, they can be used for gases and liquids. In terms of disadvantages, expensive to purchase perhaps, but probably no more so than many other bits of specialist measurement equipment, even flow meters. But one key point is that, like any other instrument, they do require careful calibration. And that's something we'll touch on in the next section. So finally, on techniques, just briefly look at a couple of others. You can use compression techniques where you measure either the change in length of the fluid by measuring the capillary rise in a tube, by using piston displacement where you force a piston into a pressure vessel containing the fluid whose density you're measuring, or by measuring the change in length of a sealed bellows filled with the fluid. In all cases, you have a measurement of the mass of the fluid in the tube or piston or bellows before you start, its initial length, and its change in length, from which you can work out change in volume and hence density. And these techniques, of course, are really only suitable for liquids. The other techniques which are available include sonic techniques, where you measure the speed of sound in a fluid. And again, there's a couple of ways where you can do that. You can do it interferometrically, using a variable path length interferometer, where you would detect the periodic impedance variation in the piezoelectric crystal oscillator, or using a diffraction grating, looking again at the periodic density variations which are caused by the sound waves propagating through the fluid. And sonic techniques can be used for both gases and liquids and across a range of temperatures and pressures. So we've looked at a range of techniques available for gases and liquids. Some are limited to liquids, some are suitable for both gases and liquids, and some are suitable for use at elevated temperatures and pressures. The oscillatory techniques are useful for general laboratory applications, for process applications, for both gases and liquids. And it's worth pointing out, of course, that if you want to achieve the highest accuracy, the lowest uncertainty, that generally implies high cost. But the corollary is not necessarily true, simply because you have a requirement for low accuracy, relatively high uncertainty, doesn't necessarily mean it will be low cost, depending on what's involved. Now, I mentioned the importance of calibration of online or inline devices, and at the start I also mentioned that in the case of the systems where you are using density to convert between mass or volume, you need to calibrate the devices traceably, because your density measurement is then part of your complete measurement chain. So recalibration at appropriate intervals is vital for maintaining that traceability. In many cases, calibration requirements are driven by regulations. That's certainly true for the oil and gas sector, for example. But it's also vital to recognize that calibration of any device, densitometer, flow meter, temperature sensor, pressure sensor, whatever, must be fit for purpose. So the calibration must achieve certain criteria, and it must ensure that the device, when calibrated, meets those requirements across its anticipated operating range. I mentioned that in the oil and gas sector, it's largely legislatively driven, and this is an extract from the 9.2 issue of the, as it was then, UK Oil and Gas Authority, now the UK North Sea Transition Authority, guidance notes for petroleum measurement, and that specifies an uncertainty in terms of dry mass for the quantity of oil being exported into a common transportation system, a pipeline, of plus or minus 0.25. So how do you achieve that? Well, when the North Sea started producing oil, the majority of flow measurement devices were volumetric flow meters, turbine flow meters to be precise. So separate measurement of density was required because to meet the regulatory requirements, as we've seen, it had to be reported by mass. And similarly, for addition to shared transportation systems, pipelines, that's allocation by mass. So fluid density is required, therefore, to convert from the volumetric flow measurement of the turbine flow meter to mass. And the most common device used is a vibrating tube densitometer. So traceable calibration of that densitometer is vital as part of the traceability of the overall flow measurement system. Quite a while back now, thinking about it, 2004 or thereabouts, an issue was raised regarding the calibration of the densitometers, because up to that time the approach had been that the manufacturer would calibrate the device when it came off the production line. Initial calibration was done at ambient conditions, 20 Celsius and 1 bar. Then measurements were made at other temperatures, at ambient pressure, to give you the temperature corrections, and measurements were made at other pressures at 20 Celsius to give you the pressure corrections. But typically when these devices were recalibrated by third-party laboratories, they were only being recalibrated at 20 Celsius and 1 bar. However, these densitometers in use are often at non-ambient conditions, up to potentially fluids at 90, 95 Celsius, and pressures as high as 130 odd bar. Furthermore, the equation used to convert from the oscillation period of the device to density is cross-coupled in the oscillation period, the temperature, and the pressure. Which kind of begs the question that was the previous calibration fit for purpose? The judgment eventually was it wasn't. So at the instigation of DEC, as it was then, predecessor to BASE indeed, and to the current Department for Science, Innovation and Technology, they asked NEL to conduct a joint industry project looking at the effects of cross-coupling, temperature and pressure cross-coupling, on the performance of liquid densitometers. And that ran from 2005 to 2009 with sponsors from all the major operators in the North Sea UK sector at that time, plus calibration laboratories and densitometer manufacturer. And the end result of that was that statement that densitometers should be calibrated at their anticipated operating conditions, i.e. simultaneously at temperature and pressure. So how do you calibrate the densitometer? Well, you use fluids of accurately known density. The fluids have to cover the full operational range of the density range of the device. They also need to cover other relevant properties, i.e. viscosity and speed of sound, because densitometers are sensitive to those. And obviously the fluid properties must be known across the full temperature and pressure range of the device. So the fluids are acting as your transfer standards there. At the start of the GIP, we asked the members, okay, what sort of range of densities and viscosities do you encounter? And they came back with a range of values. And you can see the outer box there, the full range spans quite a density range from a little bit over 500 up to just under 1200 kilograms per cubic meter. So from condensate densities up to heavy oil densities, and from light crudes up to very heavy crudes. Fortunately, we had also asked for the most common range, and that's the inner box there, which is from about 700 to 850 kilograms per cubic meter and up to about 7 or 8 centipoise. So we tried to find fluids, reference fluids, that would basically bracket that inner box. Isooctane is great as a low density, low viscosity fluid. Toluene as a higher density, low viscosity fluid. And the di-2-ethylhexyl sebacate spans higher density and into higher viscosity. The difficult one is the box down at the top left of the most common area, because from chemical physics considerations, you just don't get low density, high viscosity fluids easily. So we had to compromise, but we found 4 fluids. That's fine. We've got 4 fluids. So what we had to do was we had to characterize them to determine their density as functions of temperature and pressure. And to do that, we used NEL's primary standard liquid densitometer. It's a single sinker magnetic suspension densitometer using the Archimedes principle we saw earlier. And it can operate across a temperature range from -40 to 150 Celsius at pressures up to 300 bar. Across that full range, its expanded uncertainty at 95% confidence is better than 0.015%. And across sub-ranges, it's generally better than 0.01%. So this is what the whole system looks like. We've already seen a little bit of it previously. We've got our sinker immersed in the fluid whose density we want to measure. The buoyant upthrust is transmitted through the wall of the pressure vessel by the magnetic coupling to the microbalance. The pressure vessel sits inside a thermostat, so we can control its temperature and its pressure. And we can control them very, very well indeed. So we get very, very low uncertainties. We also have very good reproducibility on the system. Over the course of the GIP, we actually made 3 sets of measurements on the same fluid, separate samples of the fluid. The fluid was toluene, but 3 separate samples of the toluene measured at different times. As you can see, measurements in August 2007, April 2008, and September 2008. And you can see across the pressure range there up to 300 bar. I've just picked the values at 20 and 100 as the limits of the range we were looking at. The agreement between the 3 sets of data is, down at the plus or minus 0.003, 0.004%. So that gave us a lot of confidence of the performance of our densitometer. That's all well and good, but that's only our measurements. We could have a systematic error in there. So I compared with literature data, and I looked at data from PTB, German laboratory, and from NIST, the US Standards Laboratory. PTB data agree, or our data agree very well with the PTB data. The NIST data look a bit further off. They're just about at the limit, apparently, of what we would claim for our uncertainty, 0.015%. So I dug a little bit deeper into the NIST data, and what I found was, when I looked at the excellent paper they'd produced, they had actually combined data for 3 samples of fluid, what they call their standard reference material, which is the sort of sample they would normally supply to a customer to calibrate a densitometer. So that's a partially saturated sample. They also had data for fully air-saturated samples and for fully degassed samples. And the fully degassed are the blue rectangles there. Now, our system, we were using essentially fully degassed samples. So looking at this, we can see that certainly up to 80 Celsius, we're within 0.01% of the NIST values, so much closer indeed. So all of that gave us confidence in our determination of the density of our reference fluids. So having done that, how do you then calibrate a densitometer? Fill the densitometer with the fluids that you've now determined the density of, control the temperature and pressure, typically temperature stability better than 50 millikelvin, pressure stability better than 100 millibar, and measure the temperature, pressure, and densitometer output period. You'll be looking for uncertainties in temperature of the order of 15 millikelvin, pressure 20 millibar. Time period will be down in the nanosecond level. Time is the easy one to measure there. What does it look like in practice? On the left is a photo of the densitometer calibration facility with a densitometer installed in the thermostatic enclosure. The right shows it schematically, so we can control both the temperature of the fluid inside the densitometer and the air around it. We have 2 separate control systems. The fluid temperature is controlled by circulating the fluid through a heat exchanger controlled by a thermoregulator and through the densitometer. The air in the enclosure is controlled by a separate thermoregulator through heating coils and a fan. And we need to control the air temperature around the densitometer to within better than half a degree of the liquid temperature at non-ambient conditions. 20 Celsius would be okay, but we calibrate densitometers, as I mentioned, at up to 95 Celsius. And if you don't control the air temperature to within half a degree of what you're trying to achieve for the fluid temperature, you simply won't achieve the temperature stability in the fluid necessary. Obviously, we have an uncertainty budget for that. All the measurements are traceable. I've just picked an example here looking at fluid temperature of 90 Celsius and 90 bar, and uncertainty in the temperature measurement is coming out at 12 millikelvin, fluid pressure measurement at 18 millibar. Period is, fractions of a nanosecond, so we're well within the targets I mentioned earlier. So in this case, our reference fluid density uncertainty would be better than 0.01%. And we have calibrated a lot of these over the years to the procedure that became the OGA guidance procedure. As I mentioned, we can calibrate across the range from 5 to 95 Celsius up to 131 bar. Initially, what we found was that most of the units coming to us had average ADS found errors of between minus 0.1 and plus 0.1%. But the use of that average figure actually masked part of the scale of the problem initially, because whilst about 15% had negative errors of over 0.1%, almost half had positive errors of over 0.1%, i.e. a significant number of units were overreading. Interestingly, there was no clear correlation, still is no clear correlation between the as found error and the operating conditions, temperature or pressure. Just adjusting the basic coefficients in the equation as per the calibration procedure prior to 2011 when it was implemented eventually, still left about 40% of these units with residual errors of over 0.1%. Now remember, the requirements in the UK say that you have to report mass to 0.25%. So if you're using a volumetric flow meter, that 0.1% is feeding into whatever your flow meter uncertainty is. Optimizing all the coefficients, or as many as necessary over a limited temperature range, typically plus or minus 5 Celsius and plus or minus 5 bar about the nominal operating conditions, always got the residuals down to less than 0.03, usually down to 0.01%. So a good calibration. That's all well good. You've got a calibrated densitometer, which you know is performing well, but what about in use? What are the potential sources of error when you actually put it in use? Non-representative samples are an obvious one. If the densitometer is in a sample loop from the main flow line, then you have to ensure that what's flowing through the densitometer is the same as flowing through the main loop and the flow meter. Obviously, inhomogeneity of the sample in the sensor, if it's a mixture, will lead to errors. And solid deposition on the element or removal of mass by erosion will obviously influence the performance and cause either positive or negative errors. Positive in the case of deposition, negative in the case of erosion. In liquid systems, if you get gas breakout in the sensor, then that will lead to errors or even total failure to read a density. These are vibrating devices, so they are subject to stress effects, and if the associated pipework hasn't been designed properly and the unit installed properly, those stress effects can become significant. And finally, again, in the case of a densitometer in a sample loop, if there are significant temperature differences and pressure differences between the fluid flowing through the densitometer and through the flow meter, you will introduce errors unless you correct for them. Okay, calculation methods I mentioned are used, particularly they're used in a number of sectors, but particularly in the oil and gas sector, calculation methods are used in parallel with measurements. And the reason is that crude oil and petroleum products, refined products, are typically sold by volume at reference conditions, and the reference conditions are, in imperial, it's normally 60 degrees Fahrenheit and 0 psi gauge. In metric or SI, it will be 15 Celsius and standard atmospheric pressure 101.325 kilopascal. The effects of temperature and pressure on the fluid density, the volume, as we've seen, are required to convert from mass to volume, but they're also required to convert from measured to reference conditions. And over the years, volume correction factors have been developed to simplify these calculations, predating, obviously, everything being done online in real time with computers. And the most widely used implementation of these are the API, the American Petroleum Institute volume correction factors. These have a long history, the first generally recognized ones being the so-called Blue Book tables from 1952, which were then updated in 1980, and then again in 2004 as part of the Chapter 11 measurement standard. The 1952 petroleum measurement tables were called the Blue Book tables for obvious reasons, as you can see, and they were printed tables produced jointly by ASTM, the American Society for Testing of Materials, and the UK Institute of Petroleum. Although they were published in 1952, they were based primarily on volumetric data for crudes and crude fractions developed and published in 1916. And furthermore, most of the samples were actually from US domestic production in 1916. Remember, these tables were 1952. So they were updated in 1980, which had better base data, better data handling. In terms of the base data, something like 2/3 of world production and estimated reserves as of 1974 went into the base data for the revised 1980 tables. They also had better data handling with equations replacing the tables. And they were then revised again in 2004 as part of the Manual of Petroleum Measurement Standards, Chapter 11 specifically. No printed tables then, just the equations. Again, the temperature ranges and density ranges were extended, and they also introduced the combined temperature and pressure coefficients. So the combined temperature and pressure coefficients are used to calculate the effect of a temperature and pressure change from measured to reference conditions. And within the API Chapter 11 system, petroleum fluids are classified into three categories: crude oils, refined products, and lubricating oils. And the thermal expansion coefficient and compressibility is correlated in terms of a base density at reference conditions of 60 Fahrenheit, 0 psi gauge. Whilst there are several sets of coefficients for the thermal expansion coefficient, depending on the liquid density at 60 and its classification, i.e. is it a crude or refined product, etc. There's only one set of coefficients for the compressibility, so they're all assumed to behave the same way. There is an additional category called special application, which is if none of the above applies, then special application, which basically requires you to measure the thermal expansion coefficient yourself, i.e. you effectively have to measure the change in density as a function of temperature. But you can then use that with the correlations. How good are they? Well, it's worth bearing in mind that there are some limitations. The experimental data were only up to 49 bar gauge, and the assessment is that the errors are of the order of up to 0.1% at 49 bar gauge, but undefined above, as these highlighted blocks from the manual indicate. Undefined above. So for liquids, the most widely used volume correction factors are the API correction factors. They are fit for their original purpose, which is that of converting from measured conditions to reference conditions, but they certainly wouldn't be suitable for use as part of a primary measurement system. Alternative approaches can provide lower uncertainties if you are using volume correction approaches. And in general, you should review the applicability of a volume correction approach in terms of its suitability. A bit like I mentioned earlier, a calibration being fit for purpose. You need to review whether calculations are fit for purpose. Okay, that's liquids. What about gases? Well, in some respects, gases are easier because for pure components or certain mixtures, for example, pipeline quality natural gas, undoubtedly the easiest and certainly the most accurate method for determining the density is just measure the temperature and pressure, then use an appropriate equation of state. So for pure components, there's a number of packages available. NEL have our PPDS package. NIST, the American Standards Institute I mentioned earlier, have RefProp package. And depending on the implementation of the equation and the gas and temperature and pressure ranges, these equations will have uncertainties of the order of 0.02 to 0.05% in gas density, which is better than you will measure unless you are a primary standard laboratory. For natural gas mixtures, there's two main equations of state, the AGA-8 equations and the GERG 2008 equations, and they overlap. Again, uncertainties will be of the order of 0.1 to 0.5% in density, depending on temperature and pressure conditions and the composition of the gases, which of course means that for mixtures, you need to know the composition to be able to use an equation of state, either the AGA-8 or GERG or any other. And you can do that by measuring online or inline using gas chromatography, or you can take samples and do offline analysis using chromatography. If the composition isn't known, or it's out with the limits of the equation of state, then you really have no alternative but to measure using an online densitometer. The AGA-8 and GERG 2008 equations, for example, have 21 components available. If the gas you're interested in has components that are not in that, then you have to either equate them to something in the AGA-8 or GERG equation and allow for the effect, or measure. There's certainly a lot of interest at the moment in gas density because of the interest at the moment in hydrogen and carbon capture, utilization and storage. Now again, for pure CO2 or pure hydrogen, as I mentioned previously, the most accurate method and the easiest is just measure the temperature and pressure and use the equation of state, CO2, Span and Wagner, for example. Carbon capture and utilization and storage, it's unlikely to be pure CO2. There will be contaminants depending on the source of the CO2 and on the capture process. So composition determination will be required if you're using an EOS. There's interest at the moment in looking at blending hydrogen into the gas grid. So it would be blends of natural gas and hydrogen, up to 20% by volume. You don't need to change burners or the like. But again, the composition of the gas has to be known if you're using an equation of state to calculate the density of the flowing gas. It's worth also thinking about the limitations of equations of state. And my colleague, Dr. Edris Junaki, did some calculations on this, looking at 4 equations of state. So we've got the GERG 2008 and AGA-8 equations there, and a couple of other commonly used equations of state. The left-hand diagram looks okay. It looks as if they're predicting density as a function of pressure fairly well for this mixture, which is 10% by mole fraction of hydrogen in methane, so representative of hydrogen in natural gas. But if you look at the errors, it tells a different story. And you can see that the Valderrama-Patel-Teja equation, the green crosses there, is struggling as we go to higher pressures, whereas the GERG equation and the AGA-8 equation are both performing pretty well. Story is slightly different if we look at a different composition. So this is almost 20% by mole hydrogen in 80% methane. And interestingly, all of the equations there struggle in part of the pressure range. So if you're using equations of state, beware of the limitations. Also beware of the influence of density on flow metering technology. And some of that may be explicit or implicit. The humble orifice plate is an example of that. There is an explicit dependence on density, as you can see from the top equation there, because the orifice plate gives you mass flow rate, QM. To do that, it requires a knowledge of the density of the fluid. So there's an explicit dependence there. There's also an implicit dependence because the discharge coefficient has a dependence on Reynolds number, and the Gallagher-Reeder-Harris equation shown here shows that the Reynolds number dependence turns up in the equation, and Reynolds number is a function of density amongst other properties. So an implicit dependence there. Other technologies have that too. If we think about ultrasonic flow meters, there is obviously an explicit dependence if you're converting from the volumetric flow measurement of an ultrasonic flow meter to a mass flow. There's also an implicit dependence because what the ultrasonic flow meter measures is transit time along a linear path across the flow. And it then is integrated to give you the velocity. That integration depends on the flow regime, whether you are in a laminar flow regime or in a fully developed turbulent flow. So there is again an implicit dependence on density there. And as with liquids, there can be errors when you actually put these techniques into practice. So for the calculation approach, if you have non-representative samples, if you've taken a sample but it's not representative of the gas in the pipeline, then you will introduce errors. I've already touched on the equations in terms of limitations and use of inappropriate equations. Simply because you've used an equation of state for other properties doesn't necessarily mean it is the best for density for that particular mixture. Direct measurement techniques are also subject to potential errors. Solid deposition on the sensor element or erosion of the sensor element, exactly as for liquids, will give you errors. And the mirror of the liquid situation, if you get liquids in the sensor element in a gas densitometer, you will get errors. Similarly to the liquids, they are vibrating instruments, so stress effects will alter their performance. And again, if there are temperature and pressure differences between what the densitometer is seeing and where the flow meter is, you will introduce errors. So, summary. Hopefully, I have shown the importance of density for accurate flow measurement. Accurate flow measurement is used throughout process industry, and as part of that, density is needed, either for converting between mass and volumetric flow rate or as a control parameter in its own right. To do that, you need to know the density of the fluid as a function of temperature and pressure, and the density therefore becomes an integral part of your flow measurement system. And we've just seen how it also impacts explicitly and implicitly on the metering technologies. We also looked at the available techniques that can be used and the importance of calibration, appropriate calibration methods. And a brief look at calculation methods for expressing density, particularly liquid density at alternate conditions. And finally, to put it into context from NEL hold the UK National Flow Measurement Standards as part of the UK National Measurement System on behalf of the Department for Science, Innovation and Technology. And this diagram really shows how density determination sits at the core of all of these flow facilities. So it's used either for mass volume interconversions. For example, our EPAT facility uses a volumetric reference, but is used to calibrate mass flow meters. So we need density. In the gas flow facility, we have, in the oil flow facility, we have a primary gravimetric system, but we can calibrate volumetric flow meters. So we need density to convert from mass to volume there. So density sits absolutely at the core of all of the UK primary flow measurement facilities.